Hello and welcome to the 8 Notes lectures for HSC Physics for January 2024. My name is Rowan Simon and I will be covering this lecture for you guys. A bit about 8 Notes. 8 Notes has been around since 2007 and they've been helping students just like you guys thrive in their studies. They've been offering these sort of free online lectures since 2015, and they've also got a whole bunch of free resources, things like study notes, online Q&As and discussions, lectures, videos, and all these great things. So check that out when you get a chance. They also offer online tutoring through TuteSmart, and through recent Year 12 graduates are usually the tutors. They've got study guides as well. They've got Edu Unlimited, which contains a whole bunch of study guides and a whole bunch of great resources all in one place. So check that out as well. So yeah, let's jump into the content. Here's a bit about Haranish. He's the one that made these great slides for you guys. They're great, useful slides. So I believe you should be able to download these ones as well. So have a quick read about him. A bit about me. My name is Rowan Simon, like I mentioned. I also did Mathematics Extension 1 and 2, Physics, Chemistry, English Advanced, and I also did Design and Technology. I'm currently doing Civil Engineering and Physics at UNSW. So yeah, that's a bit about me. And some quick tips before we start. Anyone can be good at physics. Some people will simply require more practice than others. However, if you work hard, you will succeed. So yeah, put in the time, put in the effort, and just like many of the STEM subjects, it's all about actually getting to know your content and doing a whole bunch of practice and being able to use that content and use that theory. So being comfortable with the theory so that you can use it and apply it in a whole bunch of contexts. So when I say enjoy the content, I really do mean it, because a lot of the content that's covered in the HSC Physics syllabus is extremely useful, and even if you don't go on to do a physics or STEM related degree, it's actually quite interesting in itself. It answers a lot of questions in terms of the things that we see day to day, and it also gives us sort of a brief look into what real sort of higher physics looks like. And so I would say I genuinely mean it when I say enjoy the content. When it comes to exam techniques and past papers definitely do as many as you can. At this point, since it's January, I probably wouldn't recommend going through entire past papers timed. I mean, if you can do that, go ahead. Great. But many times, a lot of the topics you guys probably wouldn't have seen yet. So what I would recommend is going through some of the older past papers. Save the more recent ones for time practice, but if you go through some of the older past papers and pick out questions from modules or topics that you've done already, do those questions specifically, get used to the type of questions that they ask, get used to the sort of style of questions, and that's quite helpful. So past papers, and again, exam technique is very important when it comes to the actual exam. Don't stress yourself out too much. It is only just an exam, just remember that. Actually enjoy the content, and then know your content, and you'll be able to do your exam well. But exam technique, yes, is important. And different people have different exam techniques which works best for them. So try different exam techniques, especially now that you've got time before the HSC. Try different exam techniques, adapt them, change them up, see which one works best for you. Okay, so for today's lecture, electromagnetism, which is module 6, we're going to be looking at some charged particles in electric and magnetic fields. We're going to look at the motor effect, electromagnetic induction. We looked at some physics study tips, and we're going to look at applications of induction, motors, and generators as well. So please feel free to ask any questions at any time. That's what the slider is there for. So yeah, this is a pre-recorded lecture, but I will be in the live chat when the stream, so please ask anything. So let's get started. Electric charge is a property of subatomic particles. Protons are positively charged, electrons are negatively charged, and I'm sure you would have had that since, year 7 or even before that. Protons are positively charged, electrons are negatively charged. They've got both equal magnitudes of charge, but they're just opposite in sign. Now, as to answer what electric charge is, that's more of a deeper question, but it's solid enough for you guys to understand that electric charge is a property, right? It's something that, just like mass, or just like a particle has, like mass, for example, is a property of a particle, right? Electric charge is also a property of a specific particle. And things to note, all objects with a charge are surrounded by an electric field. So here's a positive charge. So here's, for example, is a proton, right? The positive charge emanates field lines outwards, right? So you have field lines sort of coming out of that positive charge, whereas in the case of a negative charge, you have the field lines going inwards into that negative charge. So whenever you draw electric fields, you would usually draw them by denoting them by arrows, right? And how densely packed the arrows are corresponds to the field strength, and the direction of the arrows corresponds to the actual direction of the electric field. So from positive charges, they emanate outwards. They're sometimes called sources, right? And sometimes negatively charged particles are called sinks because the field line sort of goes into them, like water would go into a sink. So yeah, just remember that, positive and negative charges. And another thing to note is that only other objects with a charge experiences an electric force. Electric force comes from the charges interacting with each other. So when you have a positive and negative charge, you have a force of attraction, and when you have a positive and a positive charge, or a negative and a negative charge, you have a force of repulsion. So just remember that the object must have a charge in order for them to interact through the electric field or the electrostatic forces. So just like, for example, when we're talking about the gravitational force, if you have two objects with mass, no matter how big the masses are, they attract. Whereas in the case of a charged particle, they could attract or repel. But if one is neutral, so that is zero charge, and one is positive, it's not going to do anything. So yeah, just remember that. The strength of an electric field is measured in newtons per coulomb, and I'll tell you where that unit comes from. So this gives us the formula, or if you go the other way, this gives us the formula: the electric field strength equals the force per unit charge, or F equals EQ. F, remember, is the force and it's measured in newtons. Q is the charge and it's measured in coulombs, right? That's the unit for charge, and so the unit for the electric field strength must be newtons per coulomb. And so if we rearrange this equation, the force on a charged particle is equal to the charge of that particle times the electric field strength that it's in. And a couple of examples are going to clarify this for you. So the force is in the direction of the opposite charge, by the way. So what I mean by that is if you have a positive charge somewhere here and a negative charge somewhere here, and we're looking at the force on that positive charge, the magnitude of that force is given by F equals QE, or EQ, and the direction of that force is towards the opposite charge, like that. Now, if you have two positive charges, the equation for the force, the strength of that, or the magnitude of that force, the equation still holds, this F equals QE here, but the actual direction of that force is in the opposite direction because like charges repel. Okay, so first question, calculate the magnitude of electric force on an electron positioned halfway between two parallel plates with a voltage of 10 volts between them, positioned 5 millimeters apart. We haven't quite talked about parallel plates yet, but I'll just briefly cover how you would deal with this one. But again, this lecture is meant to be sort of a crash course sort of thing, so I'm not going to go through everything in excruciating detail because we just don't have enough time for that. So what I'm going to do is just sort of quickly sketch out what parallel plates look like, give you the sort of general formula for how to find the electric field strength. Like I won't derive it or show it or sort of try and justify why it's a formula. I'll give you the formula and we'll use it. But the main thing here I want to focus on is actually finding the magnitude of the electric field force. So just like in positive and negative charged particles, for parallel plates, the direction of the electric field strength by convention is from the positive plate to the negative plate, like so. And we're going to assume that edge effects, or like in reality the field sort of bows around the edges a bit, but we're going to assume that's negligible, that the plates are sufficiently long, and usually you would have some sort of battery or something that's actually providing this actual sort of battery that's providing this this potential difference. But so first we want to find the electric field strength, because if we're going to use this formula F equals QE, we need to first find what this E is. We know we can actually find what Q is because it's an electron. An electron has always got a specific amount of charge. You can find that on your formula sheet. It's actually 1.602 times 10 to the minus 19. You can look it up on your data sheet or the formula sheet that you get given, but we need to find out what this E is. And this E for parallel plates turns out to be, assuming all the edge effects are negligible and all these other things, it's V over D. V being the potential difference or the voltage difference between them. So here it's 10 volts between them. And D is the distance between the two plates, so 5 millimeters apart. Now this is something that many students have to be careful with. Remember, if we're going to deal in SI units, we're going to make sure everything's in SI units. So 5 times 10 to the minus 3, right? When we want to convert that from millimeters to meters, so 10 divided by 5 times 10 to the minus 3 is equal to 2,000, and the unit for 2,000, and the unit for electric field strength is newtons per coulomb. And so the force equals to QE. So now that we've got an E, all we have to put in is Q, so 1.602 times 10 to the minus 19. That's the charge of an electron. It's actually negative because it's the charge, but we're only interested in the magnitude of the force in this case. But if we did have an electron in here, it'd be actually attracted to the top plate because it's attracted to the positive charge or the positive side. But for now, let's deal with the magnitudes. You've got 1.602 times 10 to the minus 19. And again, you can look that up off your formula sheet, times 2,000. And so if we put that into the calculator, you should get something like 3.204. 3.204 times 10 to the minus 16 newtons. Easy as that. That's the magnitude of the force on that electron. It's a very, very small force because the charge is very, very small. Although the electric field strength is on the magnitude on the order of like 2,000, the force in itself is very small because the charge is very small. Easy as that. And that's that for that question. Continuing on. Just give it a second to load. Okay, so magnetic fields are also vector fields. Electric fields, again, are also vector fields. As to what a vector field is, that's something a bit, that's actually a mathematical entity if you talk about vector fields as such. But magnetic fields and electric fields are vector fields, meaning that each point on, for example, if you're dealing in 2 dimensions, each point on that Cartesian plane is associated to a specific vector. It has a magnitude and a direction at every single point. So yeah, that's what a vector field in the sort of hand wavy sense is. But for now, just stick with the idea that we've got every point having some sort of strength and some sort of direction. So things to note about magnets is that they always come in dipoles. This means all magnets have both a north and south pole. So you cannot have a monopole. That is, you can't just have a north or you can't just have a south separately. And Maxwell's equations, particularly Gauss's law for magnetic fields, that helps us to sort of clarify this, or that helps us to state this very clearly, that you cannot have a monopole. Field lines also usually look like butterflies, if you want to think of it like that. You've got the field lines coming out of the North Pole and going into the South Pole. They make sort of a loop. So a loop like this. And just be careful when you're drawing these field lines. Make sure that they don't intersect themselves, because field lines cannot intersect themselves. So yeah, that's pretty much how you draw magnetic field lines. And a quick tangent on field lines. Sometimes, so it's easier to draw them like this, but sometimes you would have field lines coming into and out of the page. So what that means is, imagine if you had a north pole that was on, like, facing towards you, right? Then the field lines sort of come out of that north pole. And how do you draw that? Well, you represent them as either dots or crosses. So if you've got something that's coming out of the page, and it's a bit tricky to draw, but I'll see if I can explain what I'm trying to say. If you have, say, grab the pen. If you have, for example, the North Pole like this, and the page looks something like this, because the field lines are actually coming out that way, out of the page, if you were looking front on from the page, you would see dots. Well, if you were looking at the head of the arrows, you would sort of see dots. This is an easy way to remember it. If you got an arrow shot towards you, you would just see the point of that arrow. So you would just see like a dot. Whereas if the field lines were going into the page, then you would see crosses. You would see the back of that arrow, the sort of crosshair sort of thing on the back of an arrow. That means that the field lines are going into the page. So if you've had, instead of a north pole here, and you had a south pole, then that would mean the field lines are going into the page. You would have the field lines coming like that. Sorry about the bit of a messy drawing, but let's see if I can redraw it. If this was the south pole, we had a page here. The field lines actually come out of the north pole somewhere out here through the page into that south pole. So you would have crosses. So that's how you represent field lines going into the page and out of the page. Now, it's important to know these couple of little facts about how magnetic fields and electric fields relate to each other for the HSC syllabus. It's very important to understand that moving charges generate their own magnetic field. As to why, you can actually explain it using special relativity, but that's not something that's within the scope of the syllabus at this point. So just being able to state that moving charges generate their own magnetic field is fine. And as a result of these moving charges creating their own magnetic field, you see a whole bunch of effects or phenomenons, and that's what we're going to talk about. So the created magnetic field interacts with the external one to generate a force, and the magnitude of that force is given by this formula. And ignore the hand for now, that gives you the direction, but for now I want you to focus on this equation here. F equals QVB sine theta. So F is the magnitude of that force, Q is the charge, the label is sort of mislabeled, it should be here. So Q is the charge, the actual charge of the particle that's traveling through that magnetic field. V is the velocity of that particle, so how fast that particle is traveling, and B is the magnetic field strength, and theta is the angle of that field to the direction of the velocity vector. So what I mean by that is, suppose you have a magnetic field that's coming out of the page, like so, and you have a positively charged particle, for example, traveling into that magnetic field. Because you've got a magnetic field already, and this moving charged particle creates its own magnetic field, these two magnetic fields interact and generate a force. And that magnitude of that force is given by this equation here. But the key thing to note here is that that charge must be moving. If the velocity is 0, this whole right-hand side goes to 0, so the left-hand side must also be equal to 0. So remember that in order for this positive charge to experience a force, you have to have a velocity, a non-zero velocity. So that's how you find the magnitude of that force. Theta is the angle between the magnetic field and the velocity vector, but in this case it's 90 degrees because you have the velocity vector sort of coming outwards and you have the velocity vector going like this, so it's 90 degrees to each other. Sine 90 is 1, so you can just say QVB in this case. But if you had, for example, something that looked more like this, magnetic field was pointed upwards, velocity vector for the positive charge was at some angle like that, you'd be interested in the angle between the two vectors. That would be your theta. So the theta would be this one. So magnetic field, velocity vector, theta would be this one. But in most cases, you would want to, a good way to think about it is that we're looking at the perpendicular component of the velocity to the magnetic field vector. So when you go v sine theta, that's effectively taking this component of the velocity vector. So you just want to take the perpendicular component. I think this is best demonstrated using an example, but here is how you would find the direction of that force. So before we jump to the negative charge example, if you have your your right hand, make sure you use your right hand. There's been cases where people have used their left hand and gotten confused, but if you're using your right hand, what you want to do is point your thumb in the direction of the positive charge. So if we're looking at the first example here, you've got your thumb in the direction of the positive charge. Your fingers must be in the direction of the magnetic field. So since it's coming out of the page, I'm going to point it towards me. So it's going to look something like that. And so the palm, the direction of your palm must be downwards, or like the normal to your palm is the direction of the force. So in this case, we've got the motion of the charged particle this way, the magnetic field going this way, so the force is actually coming out of the page. It's perpendicular to your palm. An important thing to remember is it's the motion of the positive charge. So if you have, for example, a case where it's a negative charge, what you want to do is pretty much use the same rule, but you want to flip your finger. So if you, let's first point your fingers in the direction of the magnetic field. So since it's going into the page this time, because you see the crosshairs, meaning it's going into the page, and then you've got your thumb. Usually if this was a positive charge, if I can get it on camera, if this was a positive charge, we'd point it in the direction of motion to the right. But it turns out it's a negative charge, so we're going to flip our finger. So because the negative charge goes to the right, the positive charge, you can describe it as the positive charge going to the left. And then the actual force, the direction of the force is perpendicular to your palm, so it'd be coming out like this. So the force would actually be directed downwards, like that. So fingers in towards the page, your thumb opposite direction of motion, because this is a negative charge. If it was a positive charge, it'd be in the same direction, but because it's a negative charge, it's in the opposite direction, and your normal and the force is normal to your palm, so it's going to be like that. So here's how you would find the strength of the, so that's how you find the direction. This is an example where you want to find the magnitude of that force. How are we doing for time? Yeah, not too bad. So we want to find the actual magnitude of that force. So let's do that together. So you have F equals QVB sine of the angle theta. So in this case, they haven't really specified theta. So what I'm going to do is look at what the maximum force is going to be. And the maximum force occurs maximum force occurs when sine theta is maximized. And when is sine theta maximized? Well, that's when it's either 90 degrees or if you're looking at absolute value, 180 degrees. But in this case, let's just say theta equals 90 degrees. So what does that mean? It means that sine theta equals 1. And remember, if you look at the range of sine, it's between -1 and 1. So the maximum value of sine is going to be 1. Sine 90 is 1. So the force on the proton, if you go back to the question, it's actually a proton in this case. Force on the proton is equal to Q times V times B. Now Q is the charge of that proton. Now, just like we discussed earlier, the charge of an electron is the same in magnitude as the charge of a proton. It's just opposite in direction. So before we mentioned that the charge of an electron is -1.602 times 10 to the minus 19. So in this case, I'm going to say it's the charge of a proton is 1.602 times 10 to the minus 19 in the positive, or like positive. So I'm going to write that down. So Q is 1.602 times 10 to the minus 19 times the velocity vector, the magnitude of the velocity. What is the magnitude of the velocity in this case? Well, if you go back to the question, you would see that it's 1 times 10 to the 6 meters per second, or just 10 to the 6 meters per second. So it's traveling quite fast. And then now we're interested in the strength of the magnetic field, which is 10 teslas. Now, a key thing to note here is that the magnitude of a magnetic field, or like the magnetic field strength, is measured in teslas. Sometimes you will see it measured in Gauss, but teslas is a unit that's is the SI unit. So we're going to use 10 teslas. Now 10 teslas is actually a very strong magnetic field, but we'll just go with it for now. So 1.602 times 10 to the minus 19 times 10 to the 6 times 10 is 1.602. 1.602 times 10 to the minus 12. right? Minus 12 newtons. So the force on that proton equals 1.602 times 10 to the minus 12 newtons. Simple as that. You just sub in the numbers. In this case, we looked at the maximum angle, but usually they would give you the angle, or you can see it off the diagram. You just sub in the numbers, put in the charge, put in the velocity vector, velocity magnitude B being the field strength, put those numbers in, sub it in, and then you get the force on that proton. So yeah, moving on. Like I mentioned, you don't need to memorize the sine theta. If you understand what's going on here, you'll be able to see where the sine theta comes from. The key thing to note here is, now technically this is something called a cross product, and that's where the sine theta comes from, because you're looking at how perpendicular the velocity vector is. But in simple terms, if you've got a magnetic field lines looking something like that, and you've got a velocity vector that does something like this, right? The component that's parallel to the velocity, if you split this, I use a different color. If I split this into two components, you've got one that's parallel to the field lines and one that's perpendicular to the field lines, the velocity vector. So the component that's parallel to the field lines doesn't actually generate a force, or doesn't actually result in a force being generated on that particle. And the reason for that is because if you try and use this right-hand rule on something that's parallel, right, you can't really move your thumb like that. You can't have your fingers and your thumb pointed in the same direction if they're 90 degrees apart. So that means technically the cross product is going to give you a zero vector, so that this component is something that we want to ignore. So if this angle in here is theta, right, the v cos theta component is the component that generates no force, so we don't want to include that one. The only component we do want to include is a v sine theta component, because that's the only one that actually generates force. And that's what this right-hand rule tells us. If we have the magnetic field pointing upwards, the component of the velocity vector perpendicular field pointing to the right, the force is coming out of the page. So this v sine theta component is the only component that actually generates force, so we only want to take that component. So then the force is equal to Q times the component of the velocity vector that's perpendicular to the magnetic field, so v sine theta times the magnetic field strength. So it's F equals QVB sine theta, and that's where the sine theta comes from. You're only taking the component of the velocity that's perpendicular to the field, because that's the only component that contributes to the force. Now, the definition of, so like this phenomenon here, where a charged particle within a magnetic field experiences a force, that phenomenon can be used in a range of places, including motors, and that's where this name, the motor effect, comes from. But it's not specifically only for motors, it's actually for a whole range of applications, and a whole range of phenomenon is actually given the same name. So the motor effect is where a current carrying conductor in a magnetic field experiences a force. So if you have, say, this is the simplest sort of setup, where you have a north, let me fix that. Let's just say you have a north pole here, and then you have a south pole here. So this is the north, this is the south, and you have a conductor, like a current carrying conductor, so a wire for example, through this magnetic field. Because there's a permanent magnetic field here, and because there is moving electrons through this wire, you're going to have to, the wire itself experiences a force, right? And that's what's called the motor effect. You've got a current carrying conductor within a magnetic field experiencing a force. Now, hot physics tip, the sort of keywords and the, sometimes it's called jargon, but the keywords and the terminology is a very important part of forming responses, especially like long responses and things. That's what's going to be the difference between a 4 out of 5 and a 5 out of 5 responses. Even, sometimes it might be a 3 out of 5, especially for things that really do rely on the names and the terminology. So you want to be very familiar with the terminology. It should be a focus of your notes, a focus of your study, and a focus of every answer you give. You have to be very clear on what the motor effect is, what does it actually mean, and where is it? So where is it applied, or what are the different cases where you could see the effect of the motor effect, or the motor effect in itself. So why? Well, stationary electrons within a magnetic field don't experience the force because the velocity vector is 0, and so therefore you've got QVB sine theta, so it's going to be 0. But the moving electron, remember, generates its own magnetic field, right? And that interacts with the magnetic field that's already present. And that results in a force. So just like we were looking at these examples here, a wire is just a whole bunch of moving electrons, and therefore you're going to have a force on that wire, and that's how the motor effect that's how you would explain the motor effect. So moving charges are surrounded by a magnetic field, therefore a current is surrounded by a magnetic field, and you learned this in year 11. Direction of the magnetic field, you remember the right hand grip rule. The other one was right hand slap rule, it's called. The right hand grip rule, for example, gives us, for example, if there's a wire with some current going through it, the direction of that magnetic field is given by that right hand grip rule. So your thumb points in the direction of the wire and your fingers curl around in the direction of the magnetic field. So in this case, it's going to be something like that, right? All the way along the wire. And because we've got a magnetic field here and you've got a permanent magnetic field surrounding it, this wire is going to be experiencing a force because of that, because of the magnetic field interacting. Okay, so the magnetic field produced by the current interacts with the applied magnetic field, and that generates a force, and the direction of that force is given by the right-hand palm rule. So in this case, it's exactly the same rule as what we were talking about before, but in this case, if you have, for example, magnetic field like this, and the wire traveling perpendicular to it, so instead of having a singular electron, you've got a whole bunch of electrons traveling through it. Same rule applies. You've got your fingers pointing upwards in the direction of the magnetic field, current here, in the direction of the magnetic field, and then your thumb pointing in the direction of the current. The actual force comes out of the page, and so it's perpendicular to my palm, like that. And so the force would be, if you wanted to draw it, would be just a whole bunch of dots, because it's actually coming out of the page. Here's an example where you want to try and find the magnitude of that force. Now, the magnitude of that force, before we jump into that, let me explain the formula. So the magnitude of that force is given by this formula here. This gives us the direction. We're also interested in the magnitude because, remember, force is a vector. So F equals LIB sine theta. B is the magnetic field strength. I is the magnitude of the current, so in amperes, so 2 amps, 3 amps, 4 amps, whatnot. L is the length of the conductor that's exposed to the magnetic field. And theta is the direction, is the angle between the magnetic field and the direction of the current. So yeah, that's what this formula is, and I think it's best demonstrated with an example. So let's do that. So let's calculate the magnitude of the force on a 2 meter long power cable carrying 10 amps of current if it is laying at an angle of 30 degrees to a 2 millitesla magnetic field generated by an MRI machine. So let's do that. Let's first give a quick sketch of what the situation looks like. So you have a magnetic field of 2 milliteslas. It's not really giving us any directions. It's just giving us the angle between them, the relative angle between them. It's not giving us any specific direction. So I'm just going to assume the magnetic field is upwards. And the 10 amp current is passing at an angle of 30 degrees to the magnetic field. So if I put the current in, so let's just say this is a wire going through that, and there's 10 amps of current flowing through it. The angle between them is 30 degrees. And the direction of the, and the magnitude of the magnetic field is 2 milliteslas. So milli means 10 to the minus 3, so 2 times 10 to the minus 3 teslas. And that should be pretty much all the ingredients that we need to find the actual, there's one more little detail. It's a 2 meter long power cable, so we're going to say that this is 2 meters long. They actually haven't given us a diagram, so I think it's okay to assume this in this case, but whenever you do these sort of questions, draw your diagram, make it clear on how you interpret each of these values, because sometimes, if it's talking about 2 meters, right, in this case it's fairly straightforward, but you want to be clear in terms of what angle that we're talking about. Because if it's 30 degrees on the other side, then this angle in here would be 60 degrees, which is going to change your final magnitude. So you want to make sure that it's clear how you interpret each of these values. And so a diagram is going to be greatly helpful in that sort of thing. So now I think we have all the ingredients to find the magnitude of that force. So we have F equals to BIL sine theta, or ILB sine theta. F equals to BIL, BIL sine theta. B being the magnetic field strength, which is 2 milliteslas, so 2 times 10 to the minus 3 teslas. I being the current, which is 10 amps in this case. L being the length of the power cable, so 2 meters in this case, and then sine of the angle theta. Theta is the angle between the current and the magnetic field, so that's 30 degrees in this case. And so putting that into the calculator, that should give us, just to save some time, I've actually done it before, so it's 0.02 newtons. And you can double check that yourself. It's 0.02 newtons. And yeah, that's pretty much it for that question. In this case, they haven't actually asked us to find the direction of the force, but I think we can do that. It's not too tricky. If we look at the right-hand rule again, right-hand slap rule, we've got your fingers. If we've got my fingers pointing upwards in the direction of the magnetic field, and you've got the component of the current that's perpendicular to that going to the right, and so the force, again, in this case, is coming out of the page. So the force, if I use a different color, is going to be out of the page. So force on this would be out of the page like that. And remember, the dots represent out of the page. Simple as that. So this wire will be pushed towards us. Okay. Again, these sort of things aren't too complicated. They're just it's just a matter of practice and getting used to what each of these values mean, and then it's just a matter of either substituting in directly or doing a bit of algebraic manipulation and then putting in the numbers. Here's a past HSC question. I'm not sure how much time we have left in terms of, we do have a couple more topics to cover, so maybe we'll save this towards the end, and if we do have time, we'll come back to it. There is a bit of a trick to this one, so maybe I do want to save this for you guys to practice in your own time, but yeah, I think we can move on. So hot physics tip number 2, isolate or highlight key parts of the question, numbers, desired information, significant facts and terms. This will reduce silly errors, forgotten conversions, etc. And that physics tip is very useful for this particular question because many students tend to make a mistake in this question because of something very specific. Yeah, and I won't give it away too much because that's sort of the fun of this specific question. Now, the same effect can also produce forces between two wires as their fields interact. That's the motor effect we're still talking about. Because these two wires generate their own magnetic fields, they interact with each other and thus generate forces on each other. So the magnitude of that force per unit length between two parallel wires is given by this formula here, mu naught over 2 pi times I1 I2 over R. Now, don't worry too much about this mu naught over 2 pi thing. Mu naught is just a constant. It's called the magnetic permeability constant. It's about 4 pi times 10 to the minus 7. It's actually already on the formula sheet, so you don't have to memorize it. You would have already seen this in your year 11 physics content, where you were talking about solenoids, for example, uses this formula to find the magnetic field strength. But mu naught over 2 pi is the constant that usually follows these sort of questions. So if the force per unit length on that wire is equal to mu naught over 2 pi times I1 I2 over R. I1 is the current on the first wire, I2 is the current on the second wire, R is the distance between them. So here's a little diagram. So I1, again, force on the first wire, current on the first wire, I2 being the current on the second wire, D being the distance between them, and F1 and F2 being the forces between them. Remember, by Newton's third law, the actual force in itself will be equal in magnitude, but the directions will be opposite. So point in the same direction, and okay, so weirdly, if the wire's currents point in the same direction, right, the forces will be attractive. Whereas if you if they point in the opposite directions, the forces will be repulsive. And that seems a bit counterintuitive because remember, if we have opposite charges, they seem to attract. Opposite poles of a magnet seem to attract. But why does opposite charges of opposite direction of currents on parallel wires repel? It seems sort of counterintuitive. But the reason for that is because of the magnetic field. So if you look at the magnetic field on the first wire, and you use your right hand grip rule, you'll see that it goes in this sort of direction around the wire. And then if we use the same rule, but this time in the opposite direction for the I2 current, right, then you would see that it goes in this direction. So because now you see that here the magnetic field is going clockwise, and here the magnetic field is going anti-clockwise, you have two opposite. Yeah, so you have two opposite magnetic fields, and that produces a repulsion. Whereas in the case of two magnetic fields that are in the same direction, you've got the magnetic fields, both of them in the same direction, and that produces a repulsion. Here's another example. Again, this one's sort of a long-ish, so I want to save this one maybe towards the end, but we will hopefully come back to it. We should have time. Now, a quick note, the definition of the ampere was actually defined using this phenomenon, which is the force between two parallel wires. So the ampere is that constant current which, if maintained in two straight parallel wires of infinite length placed 1 meters apart in vacuum, would produce between these conductors a force equals 2 times 10 to the minus 7 newtons per meter. That sort of seems like a very wordy definition, but it very much all comes from this formula here, mu naught over 2 pi times I1, I2 over R is the force per unit length. So if we want a force of 2 times 10 to the minus 7 newtons per meter, right? So the force per unit length of 2 times 10 to the minus 7, then the current that must be placed in two straight wires, they're equal, right? Two straight wires with a distance of 1 meter apart would be 1 amp, right? So if we have 1 amp in each of them, then you'll be able to get 2 times 10 to the minus 7 newtons per meter in the as a force per unit length on those wires. So that's how 1 amp was actually defined before, until 2 years ago, which then it was revised and it was defined to be the fixed numerical value of the elementary charge to be 1.602 times, and so on, times 10 to the minus 19, where 1 coulomb is 1 ampere per second. That's it. So 1 coulomb is 1 ampere per second, and so you can use that to define what ampere is. But I think this was a very clever definition, because you can sort of very physically set it up and be like, okay, so we've got 1 meter apart. What must the current be in these two wires so that you would get a force of 2 times 10 to the minus 7 newtons per meter? Well, it turns out to be 1 amp. Okay, so Faraday discovered. So now we're going to move on to a topic called induction. And so Faraday discovered that when he passed current through a coil, a small current appeared in an adjacent coil. He got the same effect when he was moving a magnet. This phenomenon was later modeled by Maxwell as Faraday's law. So if you have, for example, if you have a battery and then a switch, and you create a sort of pulse of current, and that generates a magnetic field, it turns out that that in itself generates a magnetic field in an adjacent coil. Now, electromagnetic induction is when a conductor exposed to a change in flux induces an EMF. Now, I know that it contains a few words which may seem a bit odd to you guys, but the key question here is saying, what is flux? Well, flux is how many things are going through an area. So you could have electric flux, you could have magnetic flux, things like that. So flux density is how packed these things are, and this determines field strength. So, for example, here's a very simple definition of what flux is, or a demonstration of what it is. If you've got field lines going through a specific area, so let's say you have some plate or something, right, and that's got an area A, and the flux lines are in 90 degrees, then you've got a certain amount of flux going through it. Whereas in this case, you've got you've got two circles, right? They've both got 4 field lines. I mean, it's a bit odd to talk about field lines as discrete things, but let's say we've got 4 field lines going through it. The flux in both these things are equal, but the flux density is not same, because the density in this one is much greater than this one because of the greater area. So before we move on to what is an EMF, I think Another way to think about flux, which hasn't been included in these slides, is if you think about sort of a net, right? You have a net, like a fishing net, and it's moving through the water, right? And it's catching, so you've got some sort of net with a rectangular face, and it's moving through the water, and it's catching water as so. That sort of you could think about as flux. So you've got these water field lines sort of things, and they go into that area, and that means a flux. So that's how many things are going through an area. So if I halve this net, right, and I get rid of this half, then you've got less flux going through it. Simple as that. So flux is actually dependent on the area. And we'll come to the actual exact formula for it in a second. Another question is, what is EMF? Well, EMF stands for electromotive force, and for our purposes, we're going to assume it's the same as voltage, and so will likely induce a current. There are sort of some subtle differences between them, but for now, I think it's safe to assume that it is just a voltage, and so it will induce a current. So recapping from the previous slides, magnetic flux is the amount of magnetic field lines that go through a specific area. So if you have, say, an area, like a plate or something, and you have field lines going in through it, then it's got a certain amount of magnetic flux going through it, and it's denoted by this symbol here, phi. And magnetic flux density, however, is the same as magnetic field strength, and that's equal to how many field lines, how much flux there is per unit area. So if you have a certain amount of flux, right, that's equal to the magnetic field lines, field strength, times the area. So you could define the magnetic field strength as being the amount of flux per area, because you've got a certain amount of things going into that area. So how much is there per unit area? Well, that talks about the density, right, or the flux density. So phi equals B times A, and we'll add a little term in a second, but for now, we can say that phi, or the flux, equals the magnetic field strength times the area. So if we want to calculate the magnetic field, flux through a circular coil of radius 2 meters when a 3 Tesla magnetic field is passed through it perpendicularly, we can actually draw that out first. But before we do that, you can actually notice a slight difference between these two formulas, and that's this cos theta component. Now, why is there a cos theta component? Well, the primary reason there's a cos theta component is because the angle itself actually matters. So let's just say you have field lines going like this, in through a plate, like so, and the field lines are going in through it perpendicularly. It's a bit tricky to draw, but let's just say it's going in perpendicularly. That's like saying you have a plate like this, and your field lines going in towards them like that. That's going to mean that all the sort of net captures all the field lines going through it. But if I actually tilt this, so if this was a top-down view, let's just say I tilt that little plate so that it looks like that, but the field lines don't change, you've actually got less field lines going through it. And if I tilt it to the point where it's like parallel to the field lines, right, you've got even less field lines going through it. And because we've got pretty much zero field lines here, and the plate is sort of, the normal to that plate is perpendicular to the magnetic field lines, that means that the flux is zero. Whereas if we had the plate sitting parallel, the normal to that plate sitting parallel to the field lines, then that's going to give us maximum. And that's why we use cos theta, because when theta equals 0 in this case, because it's parallel, cos theta is maximized, so it's going to have maximum flux. Whereas if theta, so this is theta equals 0 degrees, and if theta equals 90 degrees, because the normal to that plate is perpendicular to the field lines, then cos theta is minimized, cos of 90 is 0, and so it's going to have minimum flux through it. So let's do this one here. Calculate the magnetic flux through a circular coil of radius 2 meters when a 3 Tesla magnetic field is passed through it perpendicularly. So in this case, the coil is perpendicular to the magnetic field. So let me draw that in a different color. So you've got a plate or a coil. Let's just say it's a coil. And I'm just going to draw a brief outline of that coil. And it's got wires sort of going around it, as so. And you've got field lines that are passing perpendicular through it, right? So your field lines going into it, perpendicular to it. And so in this case, the normal to that coil, which is going to come like that, is actually parallel to the field line. So theta equals to 0, so we don't have to include this cos theta component because cos of 0 is 1. So we have B times A. So flux in this case is equal to the magnetic field strength times A times cos of 0. So it's just going to be B times A. So B is the magnetic field strength, so that's 3 Teslas. And A, however, is the not just 2. Remember, A is the area, and because the radius is 2 meters, the actual area is going to be given as pi r squared because it's a circular coil, right? So pi times r squared, so 3 times pi, or 3 pi times 2 squared, oops, 3 pi times 2 squared, so 3 pi times 4, it's going to be 12 pi, and the unit for flux is actually Webers. So 12 pi Webers. So if we evaluate that or approximate that using a calculator, it's going to be approximately 37.699 or 70 Webers. Simple as that. That's how you find the actual flux through the coil. Okay, now we're going to talk about sort of an application or where this induction thing turns up, or where this flux thing actually turns up, and that's in Faraday's law. So Faraday's law states that the relative motion between a conductor and a B field or a magnetic field induces an EMF. Again, that's a whole bunch of words, so I think the best way to notice or to understand this is with an example. So here's the formula for it. The size of the induced voltage or EMF is proportional to the rate of change of magnetic flux. Notice the negative sign. This conserves the law of energy, conservation of energy, and we'll talk about that in a second. But I think the best way to look at this is through a little example. So here we've got a magnet, right? And that's coming in and out of a coil. And what that does is, if you notice the little voltmeter here, it actually generates an EMF, which in our case for now is the same as voltage, right? So this little motion of the magnet actually generates a voltage, and that results in a current flowing through this conductor or this coil. So Faraday's law pretty much describes this by saying that we've got a relative motion between a conductor, which is the coil here, and a magnetic field, which is generated by this magnet, right? We've got a relative motion here because the magnet is being moved. That induces an EMF. And the EMF, or the voltage in this case, is this one here. Now, the magnitude of that EMF is actually proportional to the rate of change of that magnetic flux. So it depends on how fast the flux changes within that conductor. So if you move this magnet faster, turns out that the voltage will be higher. The sort of peak voltage that we get here is going to be higher. If you move it slower, the peak voltage we get is going to be slower. If we increase the area, right, we're going to have a greater, I believe we're going to have a greater change in flux. Yes, we will have a greater change in flux, and therefore we're going to have a greater, and if we maintain the same speed, we're going to have a greater peak voltage. So it's dependent on the rate of change in flux. Here's a little example. I think this one's worth doing. So the diagram shows an electric circuit in a magnetic field. So we've got a circuit here, we've got a voltmeter here, and the graph shows how the flux through the conductive loop changes over a period of 12 seconds. So maybe the magnetic field's altered, or maybe the size of this conductor is altered. So initially we have 0 flux through the coil, and then we've got 0.6 Webers of flux through the coil, which stays constant between 6 and 10 seconds. And then between 10 and 12 seconds, we've got a drop of the flux, and that goes back to 0. So we're asked to calculate the maximum induced EMF within the stationary loop during the 12-second interval. That's an interesting question because we're not asked to find the EMF at some specific point in time. We're asked to find the maximum EMF. Now, if we go back to this slide here, we've noticed that the EMF is proportional to the rate of change in flux. So rate of change in flux, or rate of change of something, corresponds to the gradient or the slope. So if we look at this graph here, and remember this is flux on the y-axis, and this is time on the x-axis, the rate of change in flux is described by the gradient or the slope of each of these lines. So in this region here, we've got some slope. It's not too steep. It's not too shallow. But we've got some slope here. Here it's 0 because it's a flat line, so it's got a 0 slope. Because it's rise over run. Rise is 0. Run is sort of 2. So it's 0. Whereas in this region, we've got a very sharp drop. So even though it's a drop, it's actually very sharp. And so that means that it's got a very high rate of change in flux. So the maximum rate of change in flux actually happens in this region here. So the maximum EMF is actually given by this here. So EMF equals to minus the change in flux over change in time. So here we've got a change in flux being very rapid here, and that means that between 10 and 12 seconds is where our maximum EMF is going to be. So to find what that maximum EMF is, we're going to say, what's the change in flux? Well, it goes from 0.6 to 0.6 to 0. So it goes negative, final is 0, initial is 0.6, divided by the change in time. So it only takes 2 seconds for that to happen. So we're going to say 2. So negative is going to be positive. So we've got 0.6 divided by 2, so 0.3 volts. So the EMF that's generated is equal to 0.3 volts. So the maximum EMF, which this loop records, or this voltmeter records, is 0.3 volts because that's where the gradient is steepest, and that's what change in flux over change in time, that's what the magnitude gives us. Okay, so what about the direction of the induced voltage? Well, that's sort of described by Lenz's law. Now, Lenz's law and Faraday's law are very similar, but we've got an induced current, and so Lenz's law states an induced current must flow such that it creates a magnetic field that opposes the change in flux. Again, a whole bunch of words, but I think an example best demonstrates this. So as to where that negative comes from, it comes from Faraday's law. So understand why, it's a bit of a thought experiment. So yeah, this was Faraday's law that we looked at before. So the law of conservation of energy states that energy cannot be created or destroyed, but only transformed from one form to another. So Lenz's law is just another way of stating, or is a consequence of the law of conservation of energy. So consider we move a coil of wire through a magnetic field. So let's just say, or even better, let's just think of the same coil and magnet example that we looked at before, the animation that was on before. So we have a coil, a wire, and we have a magnet, north pole here, and we've got it being transitioned into that coil, right? So a current is induced in the wire by Faraday's law, or the coil by Faraday's law. So by Lenz's law, the negative, that is with the negative, this EMF opposes the motion of the wire. So what that means is, in our case, we've got a north pole going into the coil. So that means that it generates a field as to oppose this, because if it, and I'll show you what happens if it doesn't, but for now, understand that we've got a north pole being generated here by the current in the coil. So if we want a north pole here by our right-hand grip rule, the current must flow in this direction. And so the field actually opposes the change in flux. So we've got an increase in flux here, so it's going to oppose that by generating north pole in the opposite direction. So that means the current goes in this direction. Now, what if the current supported the change? So what if instead of opposing the change, it started going this way, right? What if we generated a south pole here, right? And the north pole was facing that way. We had a south pole on this end. Well, that's going to cause this magnet to move faster. That's going to pull it in even faster because we've got an attraction force. And that's going to create an even greater change in flux because, remember, the rate is, because we've got the magnet moving even faster, so greater change in flux. And so by Faraday's law, we're going to have more induced current because we've got a greater change in flux, or a greater rate of change in flux. And so that's going to keep going and going and going, which creates an infinite energy sort of loop, which is a real big problem because it violates the law of conservation of energy. So yeah, I guess we solve climate change or we create a black hole. Up to you. Yeah, so the key reason why we can't have the magnetic field generated within the coil to be in the same direction or to support the change in flux is because of the law of conservation of energy, which creates Lenz's law. So in this case, we've got loop of wire here within a magnetic field, right, or a ring of wire, and it originates in a magnetic field, and then it's moved out of that magnetic field. So when it's outside this magnetic field, it experiences a change in flux, because originally we've got like 4 field lines. I mean, again, we can't talk about field lines as being sort of discrete things, but we have 4 field lines, and we move it out of that. So what happens in this case? Well, because it's actually experienced a decrease in flux, it actually wants to generate a magnetic field as to try and oppose that change. So it originally goes from four magnetic lines in here to 0. So it wants to try and generate a magnetic flux that supports that, or tries to maintain that original state. So it's going to generate a magnetic field, try and do that. So that's going to be into the page, and if we use our right hand grip rule, that's going to be clockwise. That's how you would deal with these sort of problems. Now, the concept of induction is very important and has many applications. The syllabus points out a few specific examples. One is electromagnetic braking, and the other one's transformers. It's also very important in motors and generators, which we will get to in a bit. But I think it's very important, before we jump into that, to understand this concept, that the Lenz's law states that whenever we have a change in flux, the induced current forms a magnetic field as to oppose that change. That should be very clear. If it didn't, that's when we start violating the law of conservation of energy, and that's when things start to break down. So make sure that it's clear that it opposes that change in flux, and the best way to understand it, again, is through practice. There's a whole bunch of questions, past HSC papers, which rely fundamentally on this specific topic, so try and practice it as much as possible. But yeah, once we get that down, we can look at some applications. So eddy currents. Before we jump into the applications, let's talk about eddy currents, and they're just circular induced currents on the surface of flat conductors. It's nothing new, it's just Lenz's law. So instead of having specific singular wires, we now have like a surface, and we have sort of circular induced currents. So if I was to draw that, right, let's just say we have a plate which has experienced a plate of maybe copper or something, or a good conductor, and it's experienced a change in flux, right? What happens in this case? Well, it's going to experience a whole bunch of eddy currents, which are small circular loops of current like this. Now, it could be a singular large loop, or if the plate is broken down with little holes here and there, and slots, then we're going to have a whole bunch of little eddy currents. Either way, it's effectively the same as what we would see in the wire, but this time with little sort of circular currents on the surface of that flat plate. So talking about applications, here's an example of electromagnetic braking. So let's just say we have a plate or a conductive disc, and it's rotating, and we want to brake, or we want to stop that from rotating. We can place an electromagnet, so we can turn it on, and that's going to generate field lines from north to south. What that's going to do is that's going to generate eddy currents to form, because we've got now a magnetic field that's passing through it, and therefore it's going to generate eddy currents as so. And what does the eddy currents do? Well, that slows the wheel down, because eddy currents, because they're actually currents, they as a result of the resistance of the material, it causes heat to form. So it transfers kinetic energy of the actual, or rotational kinetic energy of that wheel, and it turns it into thermal energy, or heat. And so eddy currents generate their own magnetic fields, which opposes the wheel's motion. So that's Lenz's law. So yeah, then it's quite simple in that sense, because now we've got a electromagnet here, and as a result of that electromagnet, it's still spinning. So that region now experiences a change in flux, and as a result of that change in flux, it's going to go and generate eddy currents, which generates heat, and therefore transfers kinetic energy away from it and turns it into heat, so thereby slowing down the plate. Okay, so now a bit on transformers. So a transformer is a device that increases or steps up or steps down the voltage of an alternating current. So again, this is still on the applications of induction topic, but a transformer can increase or decrease the voltage. So an increase means that it steps it up, and decrease means it steps it down. So step up. There are step up transformers and there are step down transformers. But the key thing here to note is that it's for alternating current. We can't really have a transformer being used for direct current without doing some other funny stuff. But I think the key thing here to note is that if you have alternating current, we can use the transformer to step up the voltage or step down the voltage. So increase the voltage or decrease the voltage. But remember, when we increase the voltage, we're going to have to decrease the current. And when we decrease the voltage, we're going to have to increase the current. If we assume that no power is lost. So why do we have to increase current to decrease voltage and vice versa? Well, that's a result of power, right? So I think a little mathematical or just an easy math-related sort of formula-based explanation is by noting that power equals to voltage times current, right? And so in this case, if we're interested in the current, that's equal to the power divided by the voltage. So if we have an increase in voltage, that's going to mean a decrease in current. If we have a decrease in voltage, that's going to mean an increase in current, because the power always remains constant. By the law of conservation of energy, if you have a certain amount of power input, and we're not storing energy, and time's not weird, but if we have a certain amount of power input, then we have a certain amount of power output. By the law of conservation of energy, if we assume that no energy is lost, right, the power in has to be equal to the power out, and so increasing the voltage results in a decrease in current. Decreasing the voltage results in an increase in current because the power remains constant. Now, as to how transformers work, if we've got a first coil, or a primary coil it's called, and we have an alternating source of voltage or alternating current source, then when the current flows through the first coil, it generates a magnetic field. But remember, because it's an alternating current, if you think back to year 11, alternating currents keep changing direction. And because of this changing direction, the magnetic field also starts changing direction. So initially, the secondary coil, which isn't actually powered by direct voltage, initially the secondary coil, because the first coil has a magnetic field, generates a magnetic field, this secondary coil experiences a flux. And because the direction of that magnetic field changes as a result of the alternating current, the secondary coil experiences a change in flux. And so, because the alternating current keeps changing direction continuously, the secondary coil also keeps changing directions continuously, but it experiences a continuous changing flux. And as a result of that continuous changing flux, it results in an induced voltage in the secondary coil. And so that's how a transformer works. Changing the ratio of these coils is going to change the ratio of the voltages, or is proportional to the ratio of the voltages induced, and when you compare it to the source voltage. But yeah, that's pretty much how transformers work. We've got a changing current resulting in a changing magnetic field, which induces a voltage within the secondary coil, which we can manipulate in terms of the magnitude by varying the proportion of coils between them. So this is what a transformer would look like. You've got the primary winding here, or the primary coil here. We've got something called the transformer core, and we'll explain why this exists in a second. We've got the secondary coil here. So you've got the primary current input, and we've got the positive and negative terminals just like normal. And remember, it's AC. It's very important to note this is AC. Otherwise, it wouldn't work, because you wouldn't have this changing magnetic field concept. You'd only have a constant magnetic field, which wouldn't work, which wouldn't actually continuously generate a voltage within the secondary coil. Important for you guys to remember that. So we've got a primary coil, secondary coil, and it's got a varying ratio of turns. So the ideal transformer relationship is like this. Vp over Vs is equal to Np over Ns, which equals Is over Ip. Now, what do each of those variables mean? Vp is the voltage in the primary coil. Vs is the voltage in the secondary coil. Now, that ratio between the voltages is equal to the ratio between the windings on the first coil and the secondary coil. So Np is going to be this one here, Ns is going to be this one here. So Np over Ns is going to be the ratio of the secondary, the number of turns on the primary coil to the number of turns on the secondary coil. So if the primary coil had, let's say, 30 turns, and the secondary coil had 10 turns, then the ratio of NP to NS is going to be 3. So the primary voltage is going to be 3 times the secondary voltage. So for step-up transformers, there are going to be more coils in the secondary winding, and for the step-down transformers, there are going to be more coils in the primary winding. So in this case, we've got a whole bunch more coils in the primary than the secondary, so that's going to actually step down the voltage. And what does that do to the current? Well, that's going to increase the current. That's going to step up the current. So by the conservation of energy, should say conservation of energy, the voltage in, and remember this is for an ideal transformer, and what does ideal mean? It means that no power is lost to heat or other sources. We've got power in is equal to power out, so the voltage of the primary coil times the current of the primary coil is equal to the voltage of the secondary coil times the current of the secondary coil. So that's by the conservation of energy. So in reality, however, so again, this first bit we explained, and the second bit, it's inversely proportional, because remember, stepping up the voltage on the primary is going to, stepping up the voltage into the secondary is going to decrease the current in the secondary. Stepping down the voltage in the secondary is going to increase the current in the primary. So instead of going VP over VS, IP over IS, it's going to say IS over IP. So VP over VS equals NP over NS, and that's equal to IS over IP. It's going to be inversely proportional. So in reality, this equation here, or this equation here in particular, is never always going to hold perfectly, because there are always energy losses. Just like whenever we deal with normal, things on an inclined plane, for example, quite often we neglect friction, particularly in the HSC syllabus. We're going to neglect friction, but in reality, there's a whole bunch of losses. You could have friction due to contact with the ground, you could have drag, you could have a whole bunch of other losses in a range of other forms, but many times we assume they're negligible, or we assume some sort of safety factor, and that's how we deal with these sort of equations. But in reality, that's not always going to be in reality, this pretty much never holds, because there are always energy losses. So as in terms of the sources of those energy losses, we've got flux leakage. So what that means is, when we go back to the explanation of this coil, or explanation of how transformers work, we've got the flux from the first coil having to go through the secondary coil. But many times you might have flux sort of leaking, and you might not have all the flux go through the secondary coil. So that results in energy losses. You can also have eddy currents, which are induced in the core. So just like we saw in the magnetic braking example, because we've got a core, right, which is this thing here, which is pretty much, you could think of it as a solid chunk of metal, but we'll see that it's not quite a solid chunk of metal, primarily as a result of trying to minimize energy losses. But if you think of it as a solid chunk of metal, it's also experiencing a changing magnetic field going through it. And because it's going to experience a changing magnetic field going through it, it's going to result in eddy currents. So eddy currents, remember, as a result of the resistance of the material, generate heat, and so it's going to lose energy. So we're going to lose energy to heat. We're also going to have heat losses. So energy in the secondary coil is always going to be less than the primary coil, just by law of conservation of energy, just because of a whole bunch of losses in reality. Now, in terms of heat losses, what is meant by that is, when we have the current going through the wire, again, wire is not 100% non-resistive. It still has its own resistance, and so it's going to have heat. It's going to generate heat there. Now, continuing on about flux leakage, the whole reason we have a core here is to direct the magnetic flux through the secondary coil. If we didn't have this core here, we're going to have a whole bunch of flux leakage like we do have here, and that's going to result in a highly inefficient transformer. We're going to have a whole bunch of losses. So the whole reason we have this core here is as a result of, or in order to direct the magnetic flux through the secondary coil. But again, that's going to cause eddy currents, and I'll show you how we deal with that in a second. But let's do this example here first. So the primary winding of a transformer contains 2,000 turns. The primary AC voltage is 23,000 volts, and the output voltage is 660,000 volts. We're asked to calculate the number of turns on the secondary winding. Just before we start that question, just by looking at the ratio of turns, what do we know is the... So just by looking at the ratio of the windings, the ratio of the voltages, is it going to be a step up or a step down transformer? It's obviously going to be a step up transformer because we're going from 23,000 volts to 660,000 volts. That's going to be a step up. And so that means that the ratio in the secondary coil, the number of turns in the secondary coil has to be much greater than this 2,000 turns. So let's go ahead and figure out exactly how many turns there are. So we have the formula NP over NS. Equals to VP over VS, right? And so in terms of where this formula comes from, just as a side note, in terms of where this formula comes from, you can actually derive this from Faraday's law by using like sort of two applications of Faraday's law in either coil. But don't worry too much about that. For now, let's go ahead and use this formula. The primary winding contains 2,000 turns, so NP is 2,000. Primary AC voltage is 23,000 volts, and the secondary, the output voltage is 660,000 volts. So we can say NP. We're actually looking for NS. So in order to find NS, what I'm going to do is I'm going to reciprocate both sides of the equation, and that's going to help us to rearrange for NS. So VS over VP. And so that's going to give us NS equals to NP times VS over VP. Right? And NP is 2,000, so we can sub that in. VS is 660,000 volts, so we can sub that in as well. VP is 23,000 volts. That's the primary voltage. And so if we sub that in, what do we get in terms of the secondary number of coils? We get 57,391 coils approximately. We round to the nearest whole coil because it's because we're dealing with such large numbers. I don't think it's worth trying to put in how many half, or you can't really have. I mean, you can have half a coil, but it's not worth putting that level of decimal place down. So we get 57,391 coils. So in the primary coil, we've got 2,000 turns. In the secondary coil, we've got 57,391 turns. Not coils, turns, sorry. And that's going to result in a step up in the voltage from 23,000 volts to 660,000 volts. Which makes sense. That aligns with our step up voltage idea for a transformer. Yep. Okay, so we need to minimize these losses in our transformers. So remember how we talked about ideal transformers and we talked about the sources of heat or the sources of energy losses within a real transformer? Well, we want to try and minimize these losses. And that's actually a big part of this transformers topic. So we want to firstly reduce flux leakage, and by picking a good material for the core, and that's usually iron. Now that's what I talked about in terms of directing the flux through the secondary coil without having too much flux leakage. That's pretty much what it means by reducing flux leakage. We also want to reduce heat losses. Now, using an oil cooling system doesn't actually reduce heat loss as such. It just transfers heat away. The better method of reducing heat losses is probably to use conductors of lower resistance, but again, there's probably limitations on how small a gauge of wire you can use or how large a gauge of wire you can use just because of physical limitations. And so reducing heat losses isn't too easy in terms of heat losses from the actual wires itself, but we can reduce eddy currents, and that's by using laminations. So reducing flux leakage is already done by using core, but can we do something to that core so that we can still direct the flux through that, but without using but without losing too much energy in the form of eddy currents? Well, the answer to that is we can, and that's by using laminations. So if we had a solid core like this, then we would have quite large eddy currents. So we would have the magnetic field like this, and it would, or like the eddy currents would generate a large magnetic field because of the changing magnetic field as a result of the AC current through the primary coil. If we had a solid core, it would generate large continuous eddy currents. However, if we had lamination, so that what that means is we have one layer of iron, and then we have some sort of non-conductive glue or film or something between them, and then or a plate that's non-conductive between them, and that's laminated with another conductive iron component with a non-conductive glue thing in between them, and we've got a whole bunch of plates that are laminated together. That's going to actually reduce the size of these eddy currents. So these are going to be quite large eddy currents in a solid block, but having these small laminations is going to reduce the size of that size of those eddy currents. And what that does is that reduces the amount of heat that's generated and therefore increases the efficiency of the transformer. So that's why if you go to a real transformer, and you look at these cores, these iron cores, they're not actually solid blocks of iron. They're actually made of a whole bunch of laminations, all sort of glued together, plates that are glued together. Now, in terms of flux leakage, here's what would happen if we didn't have a core. Like I said before, we have a whole bunch of flux going this way, which isn't really doing anything to help us. We have a whole bunch of flux going this way. We have some flux between them, which again doesn't really help us. But when we put in a core, which looks like this, and which I was pointing out before, it actually directs a lot more of the flux through the secondary coil. Again, it's not going to be perfect. We're going to still have some flux losses on the sides, but it's going to redirect a large proportion of the flux through that secondary coil. So that's going to increase the efficiency of the transformer much greater. Now, so that's how we make transformers. That's how we reduce losses, and that's how we sort of do some rough calculations with transformers. But why do we need transformers? Well, we need transformers in order to adjust the voltage depending on what context that we need. Power distribution uses a whole bunch of transformers in a whole bunch of locations depending on what the context is, or what part of the power distribution, or what stage of the power distribution we're at. So in terms of some specific things, if you think about a washing machine, right, it uses a motor within it, so it needs some voltage. And if you think about a little LED, do these two things you need the same voltage? Well, clearly, obviously they don't. If you need to run a large motor like this, you need a much larger current, so you're going to have a higher voltage. But if you have a very small LED like this, if you run such a high voltage through it, that's just going to blow the LED. So the point here is to note that different appliances, different things need different voltages. So in order to have these different voltages, we're going to have transformers. And even the best, and in terms of power distribution, when we think about conductors, right, even the best conductors have some degree of resistance. So V1 is going to be your input voltage, and V2 is your output voltage, and you're going to have some loss, right? And the power we're going to have some amount of power lost, and that magnitude of that power, if we use power equals voltage times current, and then we use Ohm's law, you'll see that the magnitude of the power that's lost is I squared times R, where I is the current, and R is that resistance of the wire. So what we can do is, if we reduce the amount of current going through it, we can reduce the amount of power that's lost. So now remember, this is not the power that's transmitted through the wire, it's the power that's lost within the wire as a result of the resistance. So because we have some current going through it, and this wire has some resistance, right, we're going to lose power as a result of that resistance. So we have I being the current within that wire, R being the resistance, so the power lost, so I'm going to put a PL here to say power lost, is I squared times R. So if we minimize I, we're going to increase, if we minimize I, we're going to decrease the amount of power lost, which is going to make a more efficient power distribution system. So how do we do this without reducing the power? Well, the answer to that is by maximizing the voltage. And how do we do that? By using transformers. So if we step up the voltage, remember, we step down the current, even though we have the same amount of power going through it. So because we've stepped down the current, we've got a smaller loss of current, loss of power, and that means that we've got a more efficient transmission. So increasing the voltage by using a step-up transformer decreasing the current, and decreasing the current decreases the power loss due to heat as a result of this formula here, or Ohm's law. So here's sort of the continuation of that question. In terms of how we're doing for time, I think we might have time to come back and do this, but I think I want to move on. There are a couple of questions from earlier that I do want to do. We already did half this question already. This one's a bit more about power loss and things, so I don't want to spend too much time on that one. This one's a bit more on the details. So I want to jump into the next topic. So continuing on with electromagnetism, we've got motors and generators. So we can bring everything we've looked at to see how motors and generators operate. And motors and generators are everywhere. Pretty much a lot, or like the majority of your appliances use motors and generators, whether that be for cooling fans on your computer, or whether that be for, like we looked at the washing machine example with fans and whatnot. Generators are what's used to generate electricity. We'll look at details in a second, but motors use electricity to spin things, so that turns electrical energy into mechanical energy, whereas generators use spinning things to produce electricity, so that turns mechanical energy into electrical energy. So if we sort of draw an energy diagram sort of thing, we have electrical energy, so I'm going to write EE, and that turns into mechanical energy in the case of motors. Whereas for generators, we have mechanical energy turning into electrical energy. And what I mean by that is, for example, if we're looking at these cars don't look like they're electric, but if we do have an electric car, right, what we're going to do is we're going to supply that motor with electricity, and that motor is going to use that electricity to generate a torque, and that's going to make the car go forward. So we're turning electrical energy into mechanical energy by using a battery or something to store energy and sending it to a motor, thereby turning it into mechanical energy by making the car move forward. So we've got kinetic energy. Generators, on the other hand, use spinning things to produce electricity. So for example, wind turbines, right? We've got the wind that's actually turning the turbine, right? We've got the wind producing a torque on the turbine that results in turning. So if we hook it up to a generator, that turning, right, that kinetic energy is transitioned into electrical energy. So that's what generators do. So the purpose of a motor, so looking at motors in a bit more detail, the purpose of a motor essentially is to use the motor effect to generate a force. And this force then generates a torque, and the torque is used to spin whatever appliance or whatever you need to spin. So here we have sort of a schematic of the DC motors. There are a few specific components that I want to highlight here, but in essence, we've got current that goes through to a coil, and the wires on that coil have a current flowing through it, and we've got permanent magnets on either side. And so if you think back to the motor effect slide, that's going to generate a force. And because this force is off center, that's going to generate a torque. If you think about your mechanics unit, right? Remember, if you have force applied at a distance from a pivot, then we have a torque. So this force on that conductor generates a torque, and that torque is used to spin whatever you need to spin. So DC motors consist of magnets that are set up to generate the stationary magnetic field. So that's the stator. So you have the North Pole and the South Pole, and so that's going to generate a magnetic field or a permanent magnetic field. That's called the stator for the permanent, sort of non-rotating part. The current carrying coil that is free to rotate, that's called the rotor here. And you've got the split rings here, split ring commutator. So the rotor pretty much consists of the current carrying coil and the split rings, but the current carrying coil is the thing that actually holds the current, and that's the thing that experiences the force. In terms of the split ring commutator, right, that's the part that connects the coil to the external power source. So this is our external power source. So it could be, for example, a battery. Battery supplies DC. And remember, these are DC motors, so they require DC current to operate. We'll look at AC motors or AC generators in a second, but we've got DC motors here. And so we want to supply a DC current. And what that DC current does at the split ring commutator is that at this point here, it goes through this coil and around, and back through. And because it's a current carrying conductor within a magnetic field, it experiences a force. Since the force is off center, so this is the center line here, and that center line has some distance from the force there is some distance from the force to the center line, so that generates a torque, and so we can use it to spin things. The key thing here is looking at the split ring commutator. That's sort of like the part that many students get confused with. What the split ring commutator does is that it connects the coil to an external power source and it changes the direction of the current every 180 degrees. So what that means is if we spin this around 180 degrees, right, this split ring commutator makes sure that the current direction of the current stays in the same direction. Because if we have the current changing direction every 180 degrees, the motor isn't going to spin in one continuous direction. It's going to go back and forth. It's going to sort of flicker back and forth. So what we want it to do is it goes all the way around, and so now this side is going to be on this side, and so we're going to maintain a constant direction of rotation. So how does the forces produce a torque? We did talk about that in a bit. We've got the current carrying conductor with a magnetic field, and if we use our right hand rule, we've got the magnetic field going this way, current going this way, so the force is perpendicular to our palm, so it goes downwards this way, whereas the current in this side is going back towards us. So we have the direction of the current. It's a bit hard to position my hand like that, but we've got the direction of the current, got the magnetic field, and so the force is perpendicular to that, so that way. This is called a couple, or we've got like two forces that are in opposite directions but on either side of the axis of rotation, and so that's going to cause a torque or a couple, and that's going to generate the torque required to spin whatever we're spinning. So remember, just think back to your mechanics unit. Torque is the turning moment of a force, right? And so the distance from the turning point is the torque is equal to the distance from the turning point, so R times F. F is the magnitude of the force, and the sine theta is dependent on the angle between that point, that is dependent on the angle between that radial vector and the force vector. So in this case, it's 90 degrees. So that's okay. So sine theta, in this case, if theta equals 90 degrees, we have torque equals RF, because sine of 90 is 1. So in this case, it would be RF. But the reason the sine theta here is because of the fact that if we have a force, maybe I'll draw on one note just to give myself a bit more space. Just a quick recap of your module 5. If this was our pivot point, we have force applied as so. This is our lever arm, by the way. So you have R, we have force applied, and it's perpendicular to the lever arm. We have maximum torque generated. But if you think about the situation where we've got a lever arm like so, same lever arm, same distance, but this time the force is applied in the direction of the lever arm, as so. Is that going to actually generate any torque? Well, the answer to that is no. So if we have an angle of 180 degrees here, right, what happens when we have sine of 180 degrees? Well, that's 0. So the torque equals to RF sine theta, because we're only interested in the component of the force that's actually producing a torque, because anything that's parallel to this lever arm is going to not generate a torque. It's going to just, it's not going to generate anything. So we want to focus on the component that is parallel to that lever arm. So if we have a force, for example, at an angle, right, and this is our pivot point, this is our radial, this is F, this is theta, we're only interested in the component of the force that's perpendicular to that lever arm, and not the component that's parallel to that lever arm, because that parallel component is just pulling that rod. That's not going to generate any torque, only this vertical component is. So yeah, that's why this sine theta is here. This is a side note, so you're not just blindly memorizing it. You want to make sure you understand where that sine theta comes from. Okay. Oops. Now, here's a key question. What does the commutator do? Well, this is the split ring commutator that I talked about before. What does it do? Well, it reverses the direction of the current every 180 degrees as to maintain a constant flow. So what I mean by that is, in this animation, if you have a careful look, you can see that the direction of the force is always in the same direction. Right? On the left-hand side, it's always pointing downwards. on the right hand side, it's always pointing upwards. But if you look at the specific side of the coil, you'll see that at this point it's left, on the starred side, right? At this point it's down, at this point it's up. This point it's down, this point it's up. And so what the split ring commutator does is it changes the direction of that force every 180 degrees on that specific coil as to maintain a constant direction of rotation. So the split ring commutator comes in contact with what are called the brushes. These little black things here are called brushes, and they maintain contact with the commutator as to allow rotation but still conduct electricity. That's sort of their main job. But the commutator is the one that changes the direction of the current every 180 degrees to maintain a constant uniform direction of rotation. So some questions for thought. What is torque at it? Where is torque at its maximum? So is the torque maximum here or some angle in between? Have a think about that. I think I jumped the slide, but the size of the torque is dependent on the magnetic field. So the stronger the magnetic field, the greater the force on the individual conductor, and so the greater the actual torque. And just by motor effect, the dimensions, specifically the cross-sectional area of the coil, is important. And like, why is that important? Well, firstly, because if we have a longer part of the coil or a longer length of the coil within the magnetic field, we're going to have a greater force just by motor effect. But the reason that the entire area is important is because of if we draw the coil quickly. This is a top view of the coil. Now this length is important because that's the length that's within the magnetic field, right? The other length is also in the magnetic field, but it's perpendicular to the magnetic field. So, it's parallel to the magnetic field. So if the magnetic field is going something like that, it's parallel to the magnetic field, so it doesn't actually do anything if you think back to the motor effect and you think back to the right-hand rule. But the reason why this length here is important, so if I call this L1, the reason why L2 is important is because if L2 is greater, right, that increases the distance of this conductor from the center point. And remember, torque increases with greater distance from the center point. So the greater the distance from the center point, the greater the torque. And so the greater L2, the greater the torque. And so increasing L1, increasing L2 increases the actual torque. And so increasing the area, which is dependent on L1 and L2 increases the torque. The size of the current is important because, again, if you think back to motor effect, F equals to BIL sine theta. B, we talked about the magnetic field strength. Increasing that increases the torque. I is the current, so increasing the current increases the force on this individual conductor, thereby increasing the torque generated. The length we talked about because that's dependent on the area, or the area is dependent on the length. The number of turns in the coil is also important because real motors not only have just a single coil, they have a whole bunch of these coils all wrapped on top of each other. You would have 1, 2, 3, hundreds of coils, for example. And so increasing the number of turns increases the number of conductors that experiences a specific force, and so that in turn increases the torque. So the actual force on one side would be equal to BIL sine theta times the number of coils, because we have that many individual conductors within a magnetic field. The other thing that's important is the position of the coil on its rotation. So theta here is this angle in here. So if the coil is perfectly vertical, so I'm redrawing the setup here. Maybe I draw it on OneNote, sorry. I redraw the setup here. We have a north pole here. We have a south pole here. If we have a coil and it's perfectly vertical, right? This is a side-on view. If it's perfectly vertical, if you think about the current, it's actually going into the page, right? And this one's going out of the page. And so in that case, although we do have a force on each of these conductors, you'll see that since this distance from the center, this R, since the force is parallel to that lever, since it's parallel to that lever arm, so if I redraw that, this is our center, this is our lever arm, this is our force. Since the force is parallel to that lever arm, it actually generates no torque. So at this position, the torque is actually equal to 0. Whereas at this position where we've got North Pole and the South Pole and the coil being flat like so, and this is a point of rotation. Let's say we have the current going into the page here, out of the page here. If we have the force going up like this, would that be right? I think, no, sorry. Force would be, by right hand rule, you'd see the force is going up, down like this, up like this. What we would see here is that this distance here is perpendicular. The force is perfectly perpendicular to that distance, and therefore it's going to be having the maximum magnitude. So the torque is maximum at this position. So at some intermediate position, right, we're interested in what happens to that torque. Is it going to be greater? Well, I mean, I've said this is maximum, but what happens to that torque? Well, if we have something like this, we're interested in the perpendicular component of this force. So if this angle in here is theta, right, then we're interested in, and this force here is F, we're interested in F sine theta, the component perpendicular to it. So if I was to draw that on here, it's this component here. So now we've got this distance here, R, so we have F times R sine of the angle theta. So similarly, the torque is dependent on the sine of the angle theta. So at theta equals 0 degrees, torque is maximized, so that's this case here, right? And at theta equals 90 degrees, so the rotation becomes 90 degrees, torque is minimized. Sorry, other way around. Torque, in this case, theta equals 90 degrees, so torque is maximized, whereas in this case, theta equals to 0 degrees. Yep, get rid of that one. So at theta equals 0 degrees, we've got a maximum torque. Sorry, theta equals 0 degrees, we've got a minimum torque because the force is parallel to that lever arm. Whereas at theta equals 90 degrees, we've got a maximum force because the force is perpendicular to that lever arm. Maximum torque. So yeah, the size of that torque is therefore dependent on all these factors, and the actual magnitude of that torque is given by the formula. I'll let it load for a second. It's actually given by the formula torque equals to N, being the number of coils, N, times magnetic field strength, times I being the current, A being the cross-sectional area, sine of the angle theta. Theta being the angle between the force. Yeah, so you could think of theta being this angle in here, or you could think of theta being the angle between the force and the lever arm. Doesn't really matter because they're equivalent angles, so you could think of it as this angle here, theta, or you think of it as this angle here, theta. They're both equivalent angles just by geometry, but yeah, just remember that it's dependent on sine of the angle theta. Make sure you get your angle theta right. So where is torque at its maximum? We talked about that when theta equals to 90 degrees. Sine theta is maximized. Sine theta equals 1 because sine of 90 is 1. And so that would mean we've got the coil pretty much sitting perfectly flat or perfectly horizontal. So if there is no torque when the coil is perpendicular to the field, how and why does the motor keep spinning? Well, that's because of inertia, right? If we have something that's spinning and we don't apply a torque, it's going to continue spinning pretty much by Newton's first law, right? An object in motion tends to stay in motion. If you've got no resistive force, or if the resistive force is relatively small, it's going to continue spinning. So if there was no commutator to reverse the direction of the current and thus torque, what would happen? We talked about that. It would flicker back and forth because after doing one rotation, it would flip back and do like reverse because the direction of the current would now be opposite that or like in the coil would be opposite that what it originally was. So is the torque that varies in size as the motor rotates good or bad, and how do we get rid of that? I'll let you guys think about that. Is it good or bad? Well, if we want to maintain a constant torque, or we want to maintain a certain acceleration, we want to try and get a constant torque. How do we get rid of that? Well, we're going to have to sort of think about how we could position the magnetic field in such a way as to maintain a constant torque. Now, that is a bit beyond the syllabus as such, but it's still a good thing to research. Now, AC motors are practically identical to DC motors, except you don't need a split ring commutator. You have something called a slip ring commutator, and all that does is it maintains contact with the rotor. And the reason why we don't need a split ring commutator is because when we're talking about DC current, it's something like that. It's always positive, right? So this is, let's say, voltage over time. This is DC. But in the case of AC, if we're looking at the voltage over time, it's actually going to flicker back and forth. It's going to flick up, down, and so. It's actually sort of like a sine wave. It is a sine wave, pretty much. So AC current sort of flickers back and forth, positive and negative, and as a result, it causes and as a result, we don't actually need a split ring commutator. If it rotates 180 degrees and then the current itself flips direction, it's going to maintain that constant rotation, that constant direction of rotation. So all that's required is to maintain contact with this coil while it's rotating. So yeah, that's what AC slip ring motors look like. Now there are another class of motors called AC induction motors, and we'll talk about that in a bit. But for now, let's jump into something called back EMF. So back EMF is something that's induced. So back EMF is an induced current that opposes current flowing through a coil. So remember when we talked about EMF and Lenz's law and that sort of thing, we talked about how if we have a coil which experiences a changing flux, it's going to experience a change in. It's going to induce a current within that coil. So if we have a north pole, maybe I'll fix that. So let's look at an example. We've got a north pole here and south pole here. So as the supplied current goes in this direction, right? What happens is when this coil rotates, it's actually continuously experiencing a change of flux. Although the conductor is experiencing a force and it's rotating because of the motor effect, as a result of Lenz's law, the coil itself is still experiencing a change in flux. And so because it's experiencing a change in flux, it wants to try and oppose that change in flux by generating current which opposes that. So we're going to have current which opposes the induced current. Which opposes the applied current. So we're going to have an induced current, which is the blue one. And we're going to have an applied current, which is the red one. And so we're going to have a net lower current. So what the back EMF is that induced voltage which opposes the supplied voltage as a result of Lenz's law. So basically it stops the motor from whizzing off to infinity because of the fact that when you've got a greater and greater angular velocity, you're going to have a greater and greater back EMF, and so you're going to have a lower net voltage, and so that's going to stop it from having infinitely large velocity. Now, coming into generators, we've got generators are exactly as important as you think they are, whereas motors rely on the motor effect, generators rely on electromagnetic induction, so that's like Faraday's law or Lenz's law that we've been talking about. So in this case, in the case of motors, we don't really like back EMF because it slows it down because it opposes the supplied voltage. But in the case of generators, we're completely relying on back EMF. It's not quite called back EMF in generators, but the phenomenon is exactly the same. So when you spin a coil in the magnetic field, by Lenz's or Faraday's law, you've got a current that will be induced in the opposite direction of motion, and so boom, you've made electricity. So what that means is that in the case of motors, we're supplying it with a current and it's rotating, and because it's rotating, it experiences a change in flux, and so it's got an opposing voltage. But what happens if we go by hand and crank it or use a turbine or something to spin this coil within a magnetic field? Well, in that case, we've got no supplied voltage, but we're going to have an induced voltage, and that induced voltage is going to cause a current to flow, and there we have electricity formed. So generators, or like we have a flow of current, so electricity. So we have generators, right, which take mechanical energy. So we're spinning that crank, or we're using a turbine to spin that generator, and within that generator we've got a coil, and that coil is rotating within a magnetic field, and therefore we're going to have electricity, right? We're going to have an induced current. So generators very important because they are utilized to generate electricity. So whether that be through renewable sources, so when you've got other than solar, but when you've got wind turbines, wind energy, or when you've got hydroelectricity where you're relying on the flow of water to rotate that turbine, and then you use your generator, which has the coil rotating with a magnetic field, generating electricity, generating current, or in the case of even non-renewable fuel sources, when you're relying on steam, or when you're relying on coal, which heats up liquid, so steam, and therefore uses that steam to generate electricity by using a turbine, and so on. So generator is very important. An AC or a DC generator is practically identical in construction to its motor counterparts. So motors, remember, they take electrical energy supplied from an external circuit, whereas generators, they supply electrical energy to an external circuit by using energy from other outside means. So it's some sort of mechanical energy. So motors take electrical energy, turn it into mechanical. So they take that supplied voltage, rotate because of the motor effect, whereas generators, take mechanical energy in the form of rotation from wind turbines or whatnot, and they turn it into electrical energy. So the current supplied to the rotor produces a force by motor effect, which causes rotation in motors, whereas in generators, the rotor is spun by some sort of external source of energy, like I said, steam, water, etc., or wind or whatnot, and that causes the coil within that generator to spin within that magnetic field, but which by Lenz's law or by Faraday's law causes a induced current, so induction. Now, AC generators, they're much easier to construct. They've got less wear on parts and can be transformed, but they are less safe. Whereas DC generators, they're more usable, energy or power per volt, and they degrade, but they do have parts that degrade more quickly, and they cannot be transformed. Because remember, transformers rely on AC current, or the properties of AC current of a changing magnetic field, whereas DC does not supply that. Now, it almost appears that though DC generators would be superior, but the ability to be transformed is a very big deal. And remember how we talked about how important transformers were. So let's look at one more application of induction, and that's AC induction motors. So remember we talked about slip ring AC motors. This is another type of AC motor, but these are way more efficient, way more commonly used in sort of large-scale machinery and all that sort of stuff. So AC induction motors, and as the name suggests, it works by induction. It's completely different to a normal motor, but the rotor is separated from the external circuit. So what that means is, if you have a magnet, right, and you have a rotor, and you start rotating this magnet around, what happens is we've got a magnetic field, and let's say we have a singular magnet and we rotate it around a rotor. It actually starts following that because of Lenz's law. This rotor experiences a change in flux in this region, and that generates a magnetic field to oppose that. And by as suggested by Lenz's law. And so as we move the magnet around the rotor, it actually follows it. So it removes the relative motion between the two objects. So we've got a change in flux experience, and so as a result of change in flux, we've got a magnetic field. We've got a current induced within the rotor, and that interacts with this magnet as to oppose that change in flux. So it starts following that magnet, and so it starts rotating in the same direction. So AC motors pretty much make use of this phenomenon. So AC induction motors, they consist of a squirrel cage rotor and three sets of stators, stator magnets at 120 degrees from each other, and an axle. So there are something called phases. So you've got different phases for the current, and it's sort of related to when you think about sine waves and you're moving them side to side, you've got a phase shift, very much related. But what that means is we're going to start with a magnetic field here, and then this is going to sort of turn off or reduce in magnitude, and this magnetic field here is going to increase, and then it's sort of going to turn off, and then this one is going to increase and then turn off, this one's going to increase, turn off, and so on. So what it looks like to the squirrel cage rotor is that we're going to have a magnet that's sort of moving around. So this phase difference between these three sets of stator magnets is gonna in the case of the squirrel cage rotor, it's gonna look like a rotating magnetic field. And because of that rotating magnetic field, by Lenz's law, just like when we have a singular magnet, it's gonna try and oppose that change in flux by rotating alongside the rotating magnetic field. So it's gonna rotate in this direction. So as the three-phase AC current creates a rotating magnetic field, so we have a north. We have a north here and then a south here generated, and then when we turn that off, right, we're gonna have a north here and a south here generated. Turn that off, then we're gonna have a north here, south here generated. Turn that off, and keep going around and around and around. So when I mean off is because of the nature of AC, which is sort of a cycle. We're going to have a maximum and we're going to go to pretty much 0. So that's what I mean by off. And then it's going to pick back up, or like the magnitude is going to increase, but the actual direction of the current is in the opposite direction. And so it looks like a rotating magnetic field. And that causes this squirrel cage rotor to also rotate along with it as a result of Lenz's law, which is trying to resist that change in flux. And that's how a three-phase induction motor works. So yeah, that's pretty much it for today. I think I'll leave the last maybe 4 or 5 minutes to questions in the chat. But yeah, I think that's all we have for today. Thank you guys for coming. Now there are a few questions in here, which you guys can do in your own time. They're pretty good practice. They're pretty much all from past HSC papers, so give those a go. But yeah, thank you for coming. See you guys next time, potentially. See ya.